SEMs provide us with high resolution, high magnification and great depth of field. If we compare something we're familiar with the scanning electron microscope image, like a light microscope image of a bee, we can see that we're getting colour information. We've also got only certain regions of that image in focus. Our depth of field is not very great. You can see in this image that the eye is definitely in focus. It's always a good thing with a biological specimen to have the eye in focus, if nothing else. But we are limited with a light microscope in terms of that depth of field. You can see with the SEM image that we've lost the colour. We no longer have the wavelengths of light, we only have the wavelengths of electrons. And we've got a grayscale image, and we've got much higher resolution in that we can see more fine detail of the hairs or the sensilla around the front of this bee. And we've also got great depth of field, so you can see that most of that image looks pretty much in focus. So those are some of the very important gains and some of the limitations of scanning electron microscopy images. But the key to understanding magnification is really resolution. With enough resolving power we can see detail, and if we take something about the size of our thumbnail, which is roughly 1 centimetre across, and magnify it 10,000 times, it becomes the size of a football pitch, that is about 100 metres. The truth is that's a fairly modest magnification. We can usually get up to 100,000 times relatively easily on a lot of machines. What this gives you is a bit of an idea of scale and a little bit of an idea of how difficult it is going to be to actually locate the particular region of what you're interested in. You will have lost the colour of your thumbnail if you decided to put it into an SEM, and you would have to have other features that you could use to orient to particular regions. Depth of field is something we gain with a scanning electron microscope image, such as this one shown here of a fire ant. You can see if I put my mouse there, that is the modified ovipositor or the sting of this fire ant, which are a biting and stinging ant. It's been curled right round, and here we're looking at the eyes either side, and we're looking at the jaws there. And it looks very exciting and certainly all in focus. And if you look over to the right here, you'll see this particular antenna is a little out of focus. So there is a limit to that depth of field that we get with the scanning electron microscope. That specimen has been coated with a heavy metal to enhance the signal that we get, and that probably is platinum or iridium that we've used in that case. Interesting thing is here, that magnification for an SEM is very low. That's only 150 times. So we just talked about how far we can go with magnification routinely and at the extremes, and 150 times is pretty low. But still, the specimen looks exciting, and we can see features there very readily. And they have an appearance that's almost 3D. Not true 3D, but certainly three-dimensional in appearance due to that large depth of field, which is about 200 to 300 times better than a light microscope. So if we want to start at the beginning and start to understand how these electron microscopes work, a diagram like this is very useful. If we start at the top of really what will be the electron optic system, we have a filament, and it's analogous to an incandescent light bulb in a lot of ways, producing electrons, showering them out in all sorts of directions. We then control those electrons, and we produce a thin beam, a small beam, which we can shape, control using electromagnets there, represented by these horseshoe magnets. And we take that beam and we use that beam to interrogate our sample by rastering it across the sample in a rectangular raster pattern. We then collect signals that come off that sample with the detector, illustrated here as a camera, and then we present on a screen an enlarged image of that specimen. The dimension here on the screen of the width here of perhaps that insect versus the original is the magnification. So if we've got 5 times the length of the original on the screen, then our magnification is 5 times. If we think about our A4 sheet as basically the scanning pattern equivalent to the SEM image that we see on the SEM screen, we can think about this region of the sample as being divided up into pixels. So this is pixel 1,1, this is pixel 1,2. If we imagine that this pen is an electron beam, what we can do is hold it at the first pixel point and generate signal from the sample, collect that signal, and we can produce if we get a certain amount of signal, a bright point on the screen of our SEM. If we then move to the second pixel, pixel 1, 2, and get less signal from there, we get a dark point on our screen. And the way the scan pattern works is it goes across, dwells at each pixel point, gets to the end, and like an old style typewriter, comes back to the second line. Pixel point 21, 22, so on, moves across. And then when it gets to the very end, it comes right back to the beginning again. And it keeps scanning. So it's scanning point by point, line by line, screen by screen. It's a bit like having a strobe light in a dark room, having that strobe running and just moving it across the back wall to look at features and being able to see things like that. It also produces an image that's a bit like a newspaper image looked at by a magnifying glass, and when you can see that that newspaper image is made up of dots. Ideally, you want the electron beam for high resolution imaging to be about the same size as the pixel. If you overlap that pixel with too big a beam, and you can control and shape the beam and make it big or small, basically we end up with a blurry image. So what we're trying to do is make that beam size the same size as the pixels, and that gives us, for the appropriate magnification, a nice sharp image. If that's our area that we're scanning and we want to magnify a region, then what we do is we put that scan in that region. That means we change the dimensions of the scan. We do a thing called zooming in, and we fill our SEM screen up with that scan. That gives us magnification. It's just worth right at this stage considering the effect of some of these different parameters, because in an SEM, I think it's fair to say that almost everything affects everything else. If we decide we are going to scan this area and fill the SEM screen up with whatever is there, if I use my beam the same size, what's going to happen with the same number of pixels is I'm going to have way too large a beam for the size of the pixels, which really should be only that size. And it's fairly obvious that in order to avoid that blurring that we will get, we have to reduce the size of that beam so that it's now appropriate for the size of those pixels. That will reduce that blurring that we get, but we will lose signal. Our signal to noise ratio will be poorer, and basically we may end up with quite a noisy image on the screen, a speckle appearing in our scanning electron microscope image. You then might want to ask, how can I reduce that? Well, it is possible to peg back a bit of that resolution. What you could do is dwell for longer at each point. If you dwell for longer, you collect more signal, you get a nice clear, bright image of that pixel, and so on, moving through. So dwelling for longer, doing what we call a slow scan, can actually peg back some of that signal and give us a better signal to noise ratio and a stronger looking image. We call that process of scanning rastering, and you'll see some of the controls on the SEM called raster rotate and so on. Zooming in is a feature that we make use of in the SEM. It's very useful to us. Those of you perhaps who've experienced SEMs before would recognise that as you zoom in and concentrate all the energy of that beam in a smaller area, you can do some damage. You can have some charging issues and other things that we often see. But as you zoom in on a particular region of the sample and you do a focus on it, you can zoom back out again and it will hold that focus. We make use of that to give ourselves a very high quality, well-focused image. We call that process of zooming in and using about 2 or 3 times above our final imaging magnification a critical focus. It's one of a few things that we use very routinely. Talks there about the critical focus technique, talks about focus and astigmatism correction. So focusing and astigmatism are things we have to understand in terms of an SEM very well, so we'll certainly look into those in detail. But zooming in 2 or 3 times above the final image is a really good practice to do, which gives you the double benefit of sharper images and certainly flags potential images that you would see at a slow scan speed. TEMs and light microscopes don't do that. And the example that I've got on the screen here is the 7001 Joule electron microscope. It's a field emission. We can break this SEM down to an electron optics system. I mentioned that earlier, abbreviated EOS. It starts up here with the gun, has a column, and then below that is the chamber, and it is the chamber where we put our specimens in. There is an SEM computer and additional bench controls. Sometimes there's additional consoles that we use for focusing. More and more these days the SEMs have pretty much a typical PC and just a number of cards that are dedicated for the SEM. Ancillary equipment, such as used for microanalysis, can be electron dispersive spectroscopy, electron backscatter diffraction, plenty of acronyms here as you probably noticed already. They often have their own PC and they're hanging off the side of the column. So what we can see here is a bit of ancillary equipment. I'm just circling there on the side. That is a cryo unit, cryo preparation and coating unit, which is attached to that machine, therefore making it a cryo SEM. But what we might do now is have a bit of a look at the 7001 electron optic system, comprising the gun, which is inside the chamber here, fed by a high tension lead. The column runs down here. There are magnetic lenses positioned down here to control and shape the beam. Down here is the chamber. That is where our specimen is loaded into. We have a sample loading rod here, which we can insert samples in, a pre-chamber that we can use to pump down before we expose the chamber to a reduced vacuum or a poorer quality vacuum. So this is a high resolution SEM. We want to keep that quality of vacuum as high as we can in that chamber and certainly in the column. At the back here we have an energy dispersive spectroscopy set up there, and here we have a removable retractable backscatter detector. We have an aperture adjustment here. This is a physical objective aperture as they call them, and a number of other controls on the SEM. You can see components of the vacuum system here, very important. We'll look at vacuum in some detail as we go along. And basically, I think you can see in your screen, we have a number of screens there to operate the SEM, the energy dispersive spectroscopy, drives on here for stage control, so we can move the specimen up and down, round and round, back and forth and tilted and so on. So we'll look at this machine, similar machines in a bit more detail and break down some of these components and actually bring in some of them and have a look at them. It is important, as I said previously, to have some sort of idea of scale, and it's worth revising some of these nano units as I call them. And basically we're dealing mainly with microns and nanometers with SEM. So a micron is an international unit. There's 1,000 microns in a millimetre, and there's 1,000 nanometers in a micron. So while we've got this scale up here, we are sometimes working with millimetre scale size, and that would be the case with that ant I showed you previously where we're at quite low magnification. The last unit here, angstroms, really is used more in TEM. It's not an international unit, but it's used in TEM because it relates very, very well to the size of atoms. But we're mainly working with microns and nanometers. Resolution is the key to magnification. That's useful, and it can be defined as the least distance between two closely opposed points. So on this diagram here you can see really the only resolved features are in this last red diagram there, and we actually can see the gap between those two dots, and therefore we have resolved them. The eye can resolve things at about 0.2 millimeters at particular distances. Light microscope about 2.2 microns. SEM, a good SEM, 2 nanometers on the right sample, can resolve features, and a TEM, about 2 angstroms. The key to this resolution is the electron wavelength. The resolution is wavelength dependent. You can see there, if we have a large wavelength, tip to tip there, we're not going to resolve those features fully. If we've got a smaller wavelength that we're using, basically we can resolve the features as being independent. The tip-to-tip wavelength gets smaller, and so does the ability to resolve points. Comes back to Abbe's equation. Can be summarised. The smallest resolvable distance is about half the wavelength of the illumination used, and of course our illumination is electrons, and they have a very, very small wavelength and thus high resolving power, so less than 0.02 of a nanometer. It mentions there 10 kV, we've got about 0.012 nanometers resolution. At 200 kV, such as we could achieve on a TEM, certainly not an SEM, we can reduce that down to smaller. Resolution scales are useful. Again, they give us a bit of an idea of the flexibility of SEMs, and it's worth having a look at where the SEM fits amongst some of these other instruments that we use, like light microscopes and transmission electron microscopes. With an SEM, the one in red here, basically we can resolve down, as we said, to about 2 nanometers, and we can look at features on things up to about 5 or 10 millimeters even. Very flexible instrument. Worth having a look at the history of the SEM. Usually when I'm presenting this, I say, how do we get from these beautiful but fairly primitive optical light microscopes through to these high-end electron microscopes, such as this transmission electron microscope shown here. And really, we can look back at some of these pioneers and see their contribution and see where we've come from there. 1923, Bush demonstrated that we could take a beam of electrons and we could focus that by magnetic or electric fields. De Broglie developed the idea that a moving electron has wave-like and particle properties, and he also was able to calculate the wavelength of an electron. By 1932, Nolan Ruschka constructed the first TEM, 2.8 nanometer resolution. It took a little while longer to develop scanning electron microscopes. The reason I understand for this is that the scanning pattern that we use, the rastering that we use to achieve imaging in an SEM, was tried on a TEM, but the technology wasn't able to be developed. So it wasn't until 1938 that they were able to construct an SEM. The first commercial TEM became available in 1939, and in 1965 the Cambridge Instrument Company in the UK produced the first commercial SEM, and that was a resolution of about 20 to 25 nanometers, really where we use a lot of SEMs even these days routinely. So what can a scanning electron microscope do differently to a light microscope? Microanalysis is something that it can do, obviously apart from the routine high-resolution imaging that we so often recognise and use. Microanalysis can provide X-ray identification of elemental composition down to about a micron or greater in diameter. It's not nanoanalysis. We can't discretely analyse things smaller than that 1 micron with our routine microanalysis, which is energy dispersive spectroscopy, or EDS, sometimes abbreviated EDX, and that is an electron microscope image. It is a backscattered image for those of you who recognise it on the left-hand side, and we're analysing with our X-ray microanalysis this feature here, 0.03. And you can see we've produced a spectrum there with energy on this x-axis in counts per second on the y-axis. And basically what we're producing is counts of X-rays of particular energies, and to simplify it a great deal, we're effectively producing a fingerprint for a particular element. We can do a similar thing with wavelength dispersive spectroscopy, but here we're looking at energy dispersive spectroscopy. So if we just have a look at that spectra a little bit more enlarged there, that EDS spectra, you can see here we have counts per second, up to about 1,000 here. Looking at that point spot 3, you can see on the previous slide, and we've got some really nice identification for particular elements that are in this compound that we're analysing. So we've got titanium, we've got good fingerprint or signature for that, titanium K alpha, titanium K beta, peaks as we call them, X-rays of particular energies. We've got iron in that compound as well, an iron K alpha, iron K beta. So in a matter of seconds, perhaps a minute, we can very rapidly be sure that we've got those particular elements and these other elements down here in that sample. On this image here we have 3 different detectors, 2 of which are backscatter, being used to collect signal and generate an image of a TEM copper grid. So it's a specimen that is copper, and it's sitting on top of a carbon tab or background. The first part of this image, the first third or approximate third, has been taken with a secondary electron detector. So the image is as a result of that secondary electron image detector generating an image that's showing us quite a lot of the shape and topography of this particular copper grid. The next third has been taken with a backscattered electron detector collecting only the backscattered electrons. You can see we've lost a bit of the shadowing, and we can still see the shape there, but we've also got this carbon background as being very, very dark compared to the bright regions of the copper grid. And that's because backscattered electron signal gives us compositional information as well as shape information. The bottom third of this image here is also taken with a backscatter detector, but it's using backscatter topo mode. And topo mode doesn't give us any compositional difference but shows us the topography. Different types of electrons collected by different detectors gives us different imaging capabilities. To continue on with backscattered imaging, gives us compositional information that we're not getting from our standard, more conventional secondary electron image or shape related topography image. You can see that certain regions of what this sample is are bright and certain regions are dark. So what this is the tip of a fiddler crab claw. And we can see with the secondary electron image, we've got a little gap here, and because this has been, as it is typically done, coated with carbon, you can see we've got a little crack in the coating there. Seems to be a join there between the tip of the claw and the rest of the claw. When we come across to the backscattered image on the right, you can see that this tip is actually quite dark. That indicates that it's a lower atomic number average than these bright regions. And if you know anything about crabs, you'll know that their claws are made of calcium, and this region here is calcium, hard, typically hard, and the tip of this here is a different material that is actually quite soft by comparison. So this bit of research was used to generate the hypothesis that there's a soft tip on the claw, allowing the crab to do fine, gentle movement of objects without damaging it. We're using conventional high vacuum scanning electron microscopy. And for that we use electrons in a vacuum, and we produce high resolution images of samples that have been dried, coated with metal to make them conductive, and we can collect signal from those samples using detectors that collect secondary electrons or backscattered electrons. We produce monochromatic grayscale secondary electron images, typically with a striking 3D appearance, and we scan that sample point by point, line by line, screen by screen, with a focused spot or disk of electrons. We already know how to change the magnification on the screen of the SEM by changing the area of the scanned region, and we also recognise that we have to change the diameter of that probe to match that new scan size and the pixels within that. So what are some of the limitations of conventional high vacuum scanning electron microscopy? What can't it do? Well, we need high vacuum. A good quality vacuum in the SEM column in the chamber provides a free path to the electrons, a mean free path in the order of about 2 meters. We have nothing in the way blocking that electron beam, nothing in the way of atoms or molecules. We prevent high voltage discharge as a result of that high quality vacuum. We may need to coat our samples. Usually we use heavy metals such as platinum or gold, silver, some alloys, gold, palladium, iridium is another one we use very regularly, and that is to provide a high number of secondary electrons and to reduce the chances of charging, damage to the specimen, making that specimen conductive so that the electrons don't build up in there. Metals such as platinum, gold and iridium increase the secondary electron emission because they give off valence electrons very readily. For microanalysis we tend to use carbon, which is always in the system to some extent anyway, and a very light element which doesn't attenuate X-rays and block certain energies of X-rays for microanalysis. So as I said, we can use metals and we can coat those using vacuum evaporation. We can also coat carbon using vacuum evaporation. The other typical way, routine way we use metals to coat samples is through sputter coating. A nice way of looking at this, vacuum evaporation is where we change the state of that particular material, be it carbon or be it metal. It's a bit analogous to going into a bathroom, putting the hot shower on and producing steam which condenses on the mirror. Sputter coating is basically a process where we erode atoms of whatever target material we're using. We don't normally sputter carbon, but we can certainly sputter metals and alloys, and we erode that material away using a plasma and deposit it down on the sample surface. So both of these techniques coat the sample surface with a very, very fine, usually nanometer, several nanometers, tens of nanometers thick coating.